30th.
Okay, good, good. Everyone's cranking away on RSA. It's fun. It's great. RSA is the best. Ravine, any questions? Yes.
So for the third question.
Yes.
What exactly is the output of your code, like your code?
It computes. I mean, what is the Ravine function, right? So there's two different things here. There's the Ravine encryption, which who knows what that is, but there's the Ravine function. The Ravine function is basically given. So the going one way is basically just computing x squared mod n. That's the Ravine function. And the assumption is that to invert the Ravine function, so let's say this is c, right? So given c, inverting the Ravine function basically means computing a square root, one of the square roots of c modulo n. How many square roots are there of c? Right, if you pick, yeah, exactly. So there are going to be 4 of them. And so the code is going to find one. It is not going to check anything inside of the message. It's not going to look at the message. It's literally going to take this integer and find one of the 4 square roots. That's its only job. And I don't know which one it'll find, but it'll find one.
So we need to basically run it multiple times.
You might.
Okay.
Yep. You might. So if it doesn't give you a value you like, yeah, run it a few times. Do something else. Doesn't matter. That will work. Yep. Okay. So yeah. So that's the. Any other questions about that? Okay. If you're implementing RSA in real life, now we talked about RSA and some of the things it doesn't do well. What is one of the things that RSA doesn't do well that makes it not a good semantically secure encryption scheme?
It's deterministic.
What's that?
It's deterministic.
It's deterministic. And what do we do about that to fix that?
You just add random values.
Good. And we talked briefly about one way of doing that. What was the bad way? I hope I said it was bad of doing that.
But it's like flagged and then.
Yeah. Does anyone remember what that's called? I mentioned it on the exam, and it should have shown up in your readings. Anyone remember what the not so great way of making RSA randomized was called? Yes.
PKCS.
Good. Okay, so there's this thing called the public key cryptography standards. For some reason, they're called, these things are called number 1, and there are versions of this just to make life more awkward. PKCS version 1.5 defines padding for RSA signature and encryption. It tells you what to do. And the reason we care about this horrible thing we'd like to forget, it's like 20 years old, something like that, is because it's used in like all the protocols we currently use, like TLS. So every time you make a secure web connection, if you're using RSA, you're probably using this PKCS crap. You're almost certainly using it somewhat. Okay, so here's the thing. So PKCS, I think I told you how it works. You stick like a 0 at the front of your thing. You put a 20, I think it's a, oh no, it's 02, sorry. I'm going off the cuff here. 0002, I think. Don't write this down and like trust me on this. And then like, what do you put next? What are the next bytes that you put in your padding before you encrypt? This is what you do. Anyone remember?
Do they have it or something?
This is for encryption. Yes.
F.
You're thinking signature. Okay, so for signatures, the PKCS signature padding, which is a slightly different padding scheme, right? So this is encryption I care about, so this is the encryption padding. But if we were doing the PKCS, confusingly named number 1 v1.5 signature padding, we would start it with, I don't remember what the first 2 bytes are, maybe it's 01 or something, it's some other byte, something. I'm just going to put question marks here. And you're absolutely right, then we would have a whole bunch of Fs, dot, 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 and what happens next? What do we look for? How do we know we're at the end of these Fs and we're ready to do something else?
That's 0.
0 is good. We have these 0 bytes, and then what would we have? If it was a signature, what would we have?
The hash of the message.
Good. So we'd have H using some secure hash function like MD5. No, okay, not MD5. The hash of the message would go there. We talked about some ways you could screw that up, but they were stupid. Like, we're not worried about that. In encryption, what do we put instead of these Fs? What do we put here? Why would we not put a bunch of Fs for encryption? Okay, remember, the idea is we're going to have something very similar. It's actually kind of a related padding. We're going to have some stuff. It's going to end with a 0 byte. And then we're actually going to have the message, which is presumably a lot shorter than the full RSA 1024 bits or 2048 bits. So this is how PKCS padding works. What goes here? We did talk about this in class. It was in the papers you looked at.
Like random padding?
Good, random padding. So this is basically, it's if somebody, some hacker, literally said RSA isn't randomized. We need to add some randomness. So we're just gonna make up this random thing where we like stick a couple of bytes on the front, throw some random bytes, a whole bunch of random bytes, hopefully, maybe like 48 of them, like a lot of them. Then we'll use this 0 delimiter to say, okay, that's the end of our random junk, and then we stick the message we want to encrypt there. That's what PKCS number 1 v1.5 padding does. Obviously, we can't put zeros in the random padding, so it's mostly random padding. It's random padding without zeros, because otherwise things would get confusing. That's it. Okay, what's wrong with PKCS number 1 padding?
Is it because the message isn't clean, basically? Like we can just select the last part?
You might be able to do that. Like there's bad stuff that can happen, but at least on encryption it is randomized. So if you encrypt the same message 10 times, you should get 10 different ciphertexts, so that sounds much better. There's probably ways you can screw up, like verifying this or whatever. What else can happen? Yeah?
There's a padding oracle attack that
Good.
uses the fact that it's limited by 2 zeros.
Yes, and there is exactly this. So remember that RSA, and this is mentioned in the paper, but just a reminder, RSA is malleable. You can always multiply an RSA ciphertext by an integer of your choice, and there is an attack, really clever attack, where what somebody does is they use that multiplicative malleability. They take a ciphertext, and remember how you guys did your padding oracle attack on symmetric cryptos. You poked it, you mauled it, you sent it in to see if it would decrypt properly. Well, it turns out you can do almost the same thing for RSA, and what you can do is what really happens at the end of the day is you can take parts of this message and kind of shift it way over here into these bytes. And by like doing this kind of adaptive process where you do these continual tests, like a million tests, you can basically, what you get is the decryption oracle will tell you, is this a correctly structured piece of padding? When I decrypt it, do I see a 0 here? Do I see a 2 here? Do I see no zeros here? All these things. And when your decryption oracle gives you that information, you can basically maul the message to kind of like shove your message over here and move it around and gradually, bit by bit, learn what the message is. And I'm not going to go into the details of this attack. It's described in various places. It's called the Blankenbacher attack. You will see some stuff about this. And Blankenbacher attacks are literally just the same as our padding oracle attack in the sense that you get this, you get 1 bit from each decryption attempt, which is, did the padding check out or not? Now, we're going to start talking about protocols. So I want to show you what the TLS protocol looks like since we're talking about this now. Okay, so here's the TLS protocol using RSA. So there's a client and there is a server. The way I remember this, the client starts out by saying here is a random nonce, which is called a client random. And the server says here is a server nonce, which is just a random value, server random, and also sends its certificate. What's inside of a certificate? What's the real meat of a certificate? What's its purpose? What's it carry? I go to Amazon.com.
Keys.
Keys. Good. What kind of key?
I think that's public key of the server.
Good. Public key of the server. And it's signed by somebody else to prove this is really Amazon's public key. Great. Now what am I going to do if I'm using RSA encryption? You guys have 2 out of 3 moves of this protocol. What's the 3rd move going to be? What are you going to do next? You now have Amazon. You have the server's public key. You're the client. What are you going to send?
Use the server's public key and
do what? I heard somebody say encrypt.
The pre-master key with the server's public.
Good. What is this pre-master thing you just talked about?
It's for so then you take that pre-master key and both of them continue their operations on inside to get this shared session key.
But what is the pre-master key? Where'd you get it from? You just pulled it out of thin air. Where do you get it from?
I think from the random nonce that.
You actually make a new, you randomly generate a value, which is called pre-master secret. The $ always means random. You generate a random pre-master for reasons that are stupid and have to do with crypto, people talking about flipping coins. It's really dumb. You generate a 48 byte pre-master secret value on the client side, and you use RSA to encrypt under the server's public key, I'll call that PKS, this PMS value, and you send it over to the server, and the server has the secret key. It's an RSA secret key. They can decrypt PMS. They can decrypt this ciphertext to get PMS. And now how do you derive the actual key? We're going to actually encrypt real data using like AES. how do we actually get the key that we're going to use to actually encrypt real data? There's one last step. We have to derive an actual encryption key for communication. What are we going to do? This is not like a wrong or right answer. I'm just asking you guys, as engineers. You now have this random client thing, but that was sent in plain text, and everyone can see it. You have this random server thing, which everyone can see because it's sent in plain text over a Wi-Fi network. And you have this encrypted pre-master secret, which only the person, me, the client, and the server should know. Our attacker shouldn't be able to see it because it's encrypted with RSA. What are we going to do?
I think they're just going to use the pre-master secret, and then they're going to destroy it after.
Oh, okay, good. What would happen if we then went on, let's say our last step of the protocol, this is not quite how TLS works, but I think it's a good straw man. What would happen if we then used AES, like some normal encryption scheme, to encrypt data back and forth using just PMS as our key? Does anyone see any potential pitfalls here? PMS generated by the client, sent over. You're thinking about this in terms of a protocol. What would be a potential possibility? Think of this as an attacker. Yes.
Man in the middle.
Okay, what's a man in the middle gonna do?
They can intercept the encryption and then encrypt their own PMS, and then they like have the PMS. But
Okay.
The client doesn't.
That sounds interesting. Okay, but so what? What's the attack? What does that do? I'm connecting to Amazon.com, but you steal my Amazon.com connection from me and hijack it, and now you connect to Amazon.com. I mean, that doesn't seem like a really good attack, right? Because anyone can connect to Amazon.com. It's not like you're connecting as me. You're just connecting to Amazon.com. So it doesn't seem so useful, but it's good exercise.
Two thoughts. We haven't validated the identity of the client, and then with that, because we have that public key, we can now forge messages from the client to the server.
Okay.
There has to be a way to, if we're going to do anything useful, we've got to be able to forge both ways. So I keep thinking there's another part of this key that, sorry, there was an incomplete thought.
No, it's a good thought. So you're right, we haven't authenticated. We're doing one-way authentication. The server sent a certificate. We're not authenticating the client. Is that a problem?
No, I think it's optional.
Yeah, why is it optional in TLS? This is what we're talking about, by the way, TLS protocol. Why is it optional to authenticate the client? Do you authenticate yourself to Amazon.com?
Eventually, yeah. But
Eventually.
But just to read the website, no.
Yes, so just to go to a website securely, you don't need to authenticate yourself to the website, right? You go to WashingtonPost.com, they don't need to know who you are. In fact, you probably don't want them to know who you are, but you want to know you're actually looking at WashingtonPost.com. So they give you a certificate. You want to know that they're actually the right person. And the assumption is that this, only the Washington Post, if we use their real public key, which came in the signed certificate, then only the Washington Post will be able to decrypt PMS. And so when somebody talks to us using this PMS key, we'll know, hey, we must have just connected to the Washington Post. That logic seems pretty sound to me. So yes, we do not always, there's an optional way for the client to authenticate themselves, but TLS does not include it by default. Okay, but that's not the vulnerability. That's not the problem with this. What else could happen? I want you to think about something. Let's say that I see you connecting to Amazon.com, and I see you buying, I don't know, a car, because you can buy cars on Amazon, as ridiculous as that sounds. And I want you to buy 2 cars. Can I make you do that? Can I make you buy a second car? Somehow. And let's say I don't have your keys, I can't hack into your computer, I can't hack into Amazon.com, but I do have a tape recorder. And I can record, figuratively speaking, I have Wireshark. I can download, I can basically intercept and record every packet that goes back and forth between you and Amazon on this wireless network.
So can you just repeat the message?
Okay, good. So what happens if I am the attacker? So let's see if I can make this a little cleaner. So I am the attacker. I'm going to move the server over here just to make it clear, and I'm going to become your man-in-the-middle attacker here. Good. So the client random, I'm not going to change that. The server is going to respond, whoa, I don't know why I can't hold on to things today. The server responds, not going to change that. You are going to then go ahead and send this PMS over, and I'm going to pass that along the first time. and I'm gonna let you talk to the server. I'm just relaying everything, no changes. But 10 minutes after you're done talking, I am going to replay this message. I'm gonna call this C, just so I don't have to write that all again. I'll replay C to the server. I'll make a new connection to Amazon.com. And when it gets time for this third message, I replay C to the server, your C. What does that mean the server is now going to do? The server is going to decrypt that. It's going to say, okay, we've established the key PMS, the same key used in the previous session. And what happens if I then replay all of the same packets that you sent to the server during your first session with Amazon? Well, it's a good question. I'm not sure quite what's going to happen there. Like, maybe it's a problem, maybe it's not. But there's a good chance that on a website I can get you to, like, if it was a bunch of clicks and this and that, maybe I'll be able to replay your purchasing of a car. Yes?
Is that really possible though, because it's ultimately over TCP and...
Well, I'm not going to replay the TCP packets. Let's say what I'll do is I'll replay the content that was in your TCP packets. I'll just record those. I can send new TCP packets. But just the data, the HTTP stuff, I'll replay that. Yeah.
If PMS is destroyed, I don't think you can do that.
Why not?
Because you can't produce the same PMS again.
Why not? I mean, it's a ciphertext, right? I intercepted your ciphertext, encrypted under the Amazon.com public key.
Yeah, but it's going to be revoked, which means that it's not going to be valid anymore.
Where does it get revoked? Show me. Where is the system that revokes that key?
I'm saying after encryption, it should be
So you're saying that after encryption, the client should forget PMS,
both sides.
and the server should forget PMS. But if I intercepted that ciphertext, that C there, I still have that ciphertext. And if I run a new connection with Amazon.com and I replay that intercepted ciphertext back to the server, how's the server going to know that's not supposed to be something that's just a valid ciphertext?
Because PMS is invalid now.
How does it know this? You can't just say it's invalid. Give me a mechanism by which the server could check and know that.
Could the server keep some memory of the PMS?
Could, it could do that. But in practice that sucks, because think about it, you've got lots of Amazon servers, there's not just one. They'd have to synchronize their memory across all these servers. It would be really hard. Some people try that, but it wouldn't work very well. Somebody back there had a hand up? Yeah.
So every time you open the connection, you get a new client random, and so you can add non-determinism to your
I love it. How do we add non-determinism?
I guess the server could XOR the encryption and the client random, and then use that as a key phrase.
You're very close. In fact, something almost like that happens. What happens is this is called the master secret, and this is what the actual encryption keys are derived from, is computed by hashing together the client random and, I'm going to use that for concatenation, and the server random and the PMS. And the theory here is exactly what you said. Every time I make a new connection to Amazon.com, it's going to send me a different, these are big, they're like 32 bytes, a different client random. And that different client random ensures that even if somebody tries to replay an old ciphertext C from a previous session, it will not result in us agreeing on the same key. We'll get, with overwhelming probability, a very different key, and it will be different from whatever was used in the previous session. So this last step where I try to replay encrypted messages will just fail. In fact, TLS has an explicit message where it checks to see if you arrived at the same key, and if that message fails, it just barfs. Yes?
Are you going to use PMS in the encryption still, or are you going to use MS?
We're going to use MS. So MS, and actually there's one more last step I'm trying to avoid, where we derive an AES key. Well, it doesn't have to be AES, it could be something else, but whatever. And the MAC, and usually HMAC or something, or if we're using AES GCM, we can do other stuff. That's the basic idea. Okay, I don't know how I got off of this. What I was trying to talk about was this guy, Daniel Bleikenbacher, who came up with this cool attack against RSA. And the RSA handshake, what I just showed you up here, is the key handshake that's was used in TLS. Now Diffie-Hellman is used a little more commonly, but RSA is still supported and is still out there. So if I intercept this value C from your handshake, and there is a padding oracle attack, and if it's using this crazy, terrible PKCS1 scheme, What Daniel Blankenbacher showed was that you could basically make a connection to a web server, and you could replay this captured value C that you stole from somebody else's connection. And in the olden days, the servers would actually say, they would give you an explicit error that said padding error. And that padding error, by learning whether the thing decrypted or not, you could run a padding oracle attack on a TLS server. It took about a day to decrypt one TLS connection, but whatever, it wasn't the best, you could still do it. And he showed that you could basically run a remote decryption attack. You'd ultimately, at the end of this, learn PMS. Once you knew PMS, you could basically then decrypt that session and do all this bad stuff. How do you think they patched this bug? So you've got this padding oracle attack. How do you fix a padding oracle attack? Yes?
Don't say bad padding, just say bad.
Good. And what do you think happened next?
Some people implemented it and others didn't.
Everybody implemented it. Well, you're right, but I mean, eventually. Yes?
Timing attack?
Good. What's the timing attack?
Basically, it's gonna stop before if it says if it's a padding or if it's a padding, and after if it's a MAC error.
Good. So the very first thing that's going to happen is your server is going to decrypt this. It's going to look at the padding and say, is this padding, does it start with an 0002, whatever. And normally, in the old protocol, it would say, ooh, bad padding. But here, it just gives one error. It's like, something went wrong. I don't know. And that, unfortunately, even that something went wrong comes back so much more quickly than what would happen if the server went on, computing that master secret and doing all that other stuff that you could still learn. Okay, so how do you fix that? How do you add a Band-Aid to that?
Don't respond back with any error.
Okay, we already did don't respond back with a specific padding error. But unfortunately, even when we made a generic error, we got a problem. Yes?
Quantize, pretty much, like, just say, oh, there's a padding error, and then return at the very end.
Yeah, we could sit around and hope that we could make this thing, yeah, we could do that. Something like that. Something more specific. What would you do if you really wanted to make sure that it was exactly the right time? Yes?
No matter what happens, attempt to decrypt even if you're decrypting garbage, and then at the end, and if you mess something up, the padding error just said a bit that says, hey, this is invalid, and then at the end, check whether it was invalid or not, and then return after you've already done the work, even if you're decrypting garbage.
So this is pretty much what modern TLS does. It decrypts, it checks the padding. If the padding doesn't check out, it generates a random pre-master secret. It goes off to the random number generator, generates a random pre-master secret, and then it proceeds with the rest of the protocol, even though it's definitely not going to succeed with this random garbage pre-master secret. It just goes on, it derives the master secret, it then tries to send some messages back and forth using it, and the assumption is that with this random pre-master secret, the protocol will fail, but it will fail later on, and you won't know exactly whether it was because of a padding oracle or something else that went wrong. And so this is the current protection that's in TLS today. What's wrong with it? Where do you see an avenue for a timing attack? Yeah.
Generating the random number.
Good. What is involved in generating a random number? What do you have to do?
Watch coin flips.
Okay, who's flipping the coins though? Where do you get random numbers from on your Unix or Windows system?
It's
Yeah,
a
but
timestamp. I mean,
Please don't use a timestamp.
I
Let's
mean,
not do that.
Well, I mean, you have some kind of pseudo-random function that takes known sources of entropy,
Okay.
mangles them all up, and then spits it out.
Who does it? Which part of the system does that?
Typically, I guess the operating system or a library.
Good. Okay. On Linux, anyone know where you get random numbers from specifically as a developer?
urandom?
Good. There is a device, and it's on Macs too. Dev urandom.
U is random, don't you, not urandom?
Well, that's a good question. There's also a device called dev random. What's the difference between these devices?
The U.
Random doesn't block.
The U is definitely a difference. Okay, good. What is the difference? All right, so somebody said it doesn't block.
Right.
Okay, what does that mean?
Random entropy, urandom is still going to keep giving you numbers. So random means that it will still be random, you'll still be getting random entropy, and urandom means it'll just spit more garbage out.
Okay, so these are different things. So somehow these operating system is collecting unpredictable stuff that's happening on your system. Wait a second. What is unpredictable that's happening on your computer?
Electrical noise from components on the board itself.
Possibly, sure. What else?
Your keyboard, your mouse movement.
Yeah, maybe. Good. Okay, what else? What else?
Cosmic rays.
Possibly. Actually, I'm not kidding about this. Google does tests on the memory in their data centers where they look for random failures that happen to, like, especially the AES encryption, and they were actually able to build like one of the world's larger cosmic ray telescopes just by finding those kind of random errors and categorizing them. Like, cosmic rays don't really affect your computer, but when you're Google, they add up. So it's a real thing. But yes, okay, random stuff that happens. What else? What other things that are definitely going to happen in your system do you have? Anyone have a hard disk anymore? Like a spinning one? Yes? Okay, 2 people in this class have a spinning hard disk. Okay, spinning hard disks, good source of entropy because the time it takes to move from one sector to another is actually dominated by a lot of kind of chaotic error movements down near the hard disk read head. So people would compute that. They would take the low order bits of those timing measurements and they would throw them into here. So there's all different. Some people use network packets, although that's dangerous because you don't always control the network. Okay, so lots of stuff goes into this, and it gets munged together using hash functions, and ultimately you can read from one of these just like it's a file. And then what's the difference between these two? Somebody said blocking, yes.
So if you ran out of entropy, you have to go get some more, and if you ask urandom for more bytes than you have entropy to back up, it will just give you as many bytes as you ask for, no matter if they're random or deterministically generated by the algorithm behind it.
Good, okay.
Random will give you only as much bytes as it can guarantee are backed up by entropy.
Good, so random will block. If you don't have enough entropy in your system, random will block. You will do an fread or whatever your read command is, and it will pause your entire process, your entire application, until such time as it has enough randomness to give you what you want. Which means if you're generating this PMS value using dev random, there's a very good chance that when you go to make this random fake PMS, your system will actually block, maybe even for like several milliseconds while the system kind of catches up on entropy. So that creates a timing channel. So you don't want to do that. You want to use dev urandom, but there are other reasons that can create problems too, even very small timing channels and so on. So anyway, these things really matter. Now, what I wanted to talk about very briefly today was a new really stupid vulnerability that some colleagues and I were looking at. And since we're here talking about TLS, it's a good introduction to it. Okay, we've been talking about randomness for the last couple of minutes. And you guys said, where do random numbers come from? And some people said dev urandom and dev random. But what's underneath the hood of dev urandom? How is it generating all of these random numbers from what has to be a very small amount of actual unpredictable stuff happening in your system? You can generate gigabytes of output from dev urandom, but you're only getting a few hundred bits per second tops of like unpredictable stuff happening from keystrokes. How does something like dev urandom make so much more entropy? Yes?
It takes bits from dev random and then it uses a probabilistic random number generator to spit out more.
Good. It actually uses something called a deterministic random number generator. So a pseudo random number generator is another word for this. Okay, pseudo random. And what a pseudo random number generator does, I'm going to come back to protocols in a little bit. It is an algorithm, let's call it P, that takes in a short seed, X, and spits out a long, generally much larger, long stream of, I'm going to put quotes around random, let's call it random looking bits. So basically, it's an algorithm. Of course, algorithms in this sense, I mean, by definition, since we don't really have any other randomness except this X, it's a deterministic algorithm that takes in X and stretches it into a very long string. Now, you guys have seen ways to do this already in this class. How would you go about making a long stream of random-looking numbers from a relatively short, truly random input, using just the tools we've talked about here?
Hashing.
Good, hashing is a great one. So you could hash X. What would you give me an actual construction? How do I turn X, let's say X is 256 bits long. How do I turn X into a gigabyte of random looking numbers using a hash function? Anyone?
Like take the output of a hash and put it into the hash and then.
Okay,
like,
good. So your construction is, let's say, xi is equal to hash of xi minus 1. Is that about right? Or did I mean, it's fine. Okay.
And then you're concatenating xi minus 1, xi, and so forth, right?
Yeah.
Okay. I mean, you might have some problems here, right? Because if I give you this hash of xi minus 1 and hash of xi, you can always compute one from the other. So whatever, maybe we could do something. We'll come back to what something is. Okay, maybe we output like part of it and we keep half of it. But yeah, okay, sure, I like this. So we could do something like this where we cycle the input into the output and we use a hash function to kind of produce a long string of these things. If we assume our hash function has some really good randomish looking properties, probably like SHA-256, the outputs will look really random. Okay, I mean, leaving aside this construction is a little wacky, but whatever. Okay, give me another idea. How else would you do it? Could be hash functions, but give me a different construction. Yeah.
A Mersenne twister?
Yes, but what's the problem with that?
It's
So-
fully deterministic, and if you have a few inputs, you can then generate all the future numbers.
Good. So there are a lot of people who generate random numbers using insecure algorithms. The one you just named is the Mersenne twister, is the default pseudo-random number generator in Python. We don't use that because there's an attack on it that basically allows you, given just some output bits, to predict all future output bits. So there are non-cryptographic random number generators we don't want to use to generate stuff. And why don't we want to use those to generate stuff? Looking at the TLS protocol, if I implement this using the Mersenne twister on my client side, and you know that there's an attack where if you see some random output from the client, you can predict later outputs, what's going to happen to you?
You see some random output going over to the server and then determine what PMS is.
Good. So presumably this client random is generated by the client from the random number generator. And then a little bit later, the client's going to generate PMS using the same random number generator because we're lazy, right? And then it's going to encrypt that. You're not supposed to know PMS if you're an attacker. You're not supposed to be able to read this. But if you saw a client random, you got 32 bytes of output from that generator, maybe that's enough for you to like break the generator and predict what its later outputs are going to be, and now you could basically know PMS without even being able to decrypt RSA, and you've won. And you could basically decrypt that whole connection. This is really, really important. If you have a bad random number generator that is predictable, then somebody who sees client random may be able to predict PMS, and your whole protocol breaks. So you don't want to use a bad random number generator. Okay, give me one more example of a good random number generator using cryptographic functions. Yes?
Like the conjure mode on a...
Good. I was hoping somebody would say that, okay? So we'll say xi is equal to, we could use AES, sounds good to me, under some key, which we have to have. Maybe we'll have, let's do this differently. We'll call it output I is AES under x as the key, because we had x being random anyway, of a counter, which we'll call I. So we say for I equals 0 to as much stuff as we need, we just compute the AES counter stream cipher by enciphering 0, 1, 2, 3, 4, 5, and concatenating those outputs, and that gives us our output. Good, this seems great. Can anyone see any problems with this? Yes?
Would it take a long time to do this?
It's just one cycle of AES per block, per 16 bytes, you get output. It would take longer than the Mersenne twister, you're right, but it's worth it for, you know, this kind of a good, high-quality output. Yes?
Recent benchmarks for AES encounter would actually show that it's just as fast as, actually it's like twice as fast as a Mersenne twister because of SIMD and specialized Intel instructions.
Good, so there are special Intel, on modern Intel processors, there are actually specialized instructions for computing AES. So if you have one of those processors, this is actually even faster than Mersenne twister. So this is awesome, great. What bad thing could happen that you could see potentially happening that would make you worried? Now this is not an attack, this is actually a perfectly fine way to generate random numbers, but let's say somebody hacked into your system. You're making lots of TLS connections, your dev random was computing this over and over again, just computing, always incrementing I. What bad thing could happen if somebody hacked you? What could they learn that would be very, very bad for you? Okay, if they learned I, but maybe I is not a big secret, right? If I just increments, it won't be a killer, but they might need it later. What else?
The key to the AES, I mean,
Good. If you use the same key forever, like if you boot up your computer, you use the same key, you shut down your computer, save it to disk, and so on, and somebody gets this key, you're toast. So you need to generate a new key, and if somebody hacks into your computer, scrapes memory, gets this key, once again, you're toast. And you're toast in a really bad way, because if you keep the same key for a long time, and you're right, somebody gets I, they can rewind and go back in the past and find out what random numbers you used in the past and decrypt anything else you encrypted like 10 days ago or 20 days ago. Which brings me to a specific construction that I actually wanted to show you guys. So in their infinite wisdom, there is this group called NIST, this government agency called NIST, that standardizes crypto. And if I can get this to come up, give me 2 seconds. And they have very specific opinions about the types of random number generator that you should use. And I want to show you a picture of one of their constructions. This has been deprecated, but for years they recommend people using it. Why can't I get this to come up? Here we go. Let's see if I can zoom in on this. Okay, well, while this is booting up, I'll see if I can draw it. Okay, so the construction is, please start up. There it is. Okay, here's the construction. Let me see if I can make it bigger. Okay. So NIST came up with this generator. It's actually part of an ANSI standard, X9.31. It doesn't matter. The basic idea is, first of all, you'll notice it uses AES. Okay, so just like the counter mode thing we had before, uses AES to generate random numbers. Let me show you what's happening here. There's a fixed key K that is never changed. Once you start this generator up, you choose a K, and you use K forever. First detail. Okay, so the next thing is these RI values. This is the output of the generator. So the input to the generator is this value V, which is called the current state of the generator. What happens is you take V, and you take this T value, which is a timestamp. That just comes off your system clock. You take this V value, or you take this T value, you feed it through the AES function, you take the output, and you XOR that with your current state value, V, VI minus 1. Okay, you now feed the resulting XOR through AES using the key K, and that produces your output, your 16 bytes of output. You also take that value up here, and you XOR it with the result of this AES encryption of the T value, and then take that whole mess and feed it through AES one more time to get a new V value. And then the next time you want to generate an output block, this V value becomes this one, and you just repeat. Okay, if it looks confusing and stupid, that's because it is kind of confusing and stupid. It's like, what are you doing? There's all this crazy stuff going on. We just showed you can use AES counter to generate this stuff. Why would you do all this nonsense? Okay, so the question is, let's imagine somebody has broken into my computer and stolen the value K. And you are able to see at least one output block, RI, from this generator. Is there anything you can do that would compromise this system? Follow it through. So you've got RI, you've got K. What could you do to go backwards and recover the internal state of the generator? Is there an attack here?
You could XOR it with, or, never mind.
No, you good.
I was gonna say you could XOR it with DI and then decrypt that that's the wrong order.
Oh yeah. No, this RI is what's coming out of here.
Yeah.
Yes.
If you decrypt RI and then XOR RI decrypted, you get the encrypted TI. So you can find TI.
Good. So we can take this RI, which we got from, maybe it came out of a client random in a TLS protocol. We got this RI. We know K somehow. I've hacked your K. I can use, this is AES encryption, but AES is invertible. There's a decryption operation too. This is AES, by the way, in ECB mode. It's just using the AES cipher. I can take this 16 bytes. I can work backward through this AES encryption using K, and I get to here. And you're saying what now?
XOR that with the original RI.
Okay, where does the original RI come from? Because remember, what this gets XORed with is this
Or read an arrow backwards.
Yeah. Okay, we go this way. We get to this is the decryption of RI. What do I XOR? I want to get to VI. That's the state. What do I do to get from here to here? What am I missing? Yeah.
Well, why can't you go from the top where VI is and decrypt that with 10, and then...
Okay, so VI is the internal state of the generator. It's not output. It's just kept inside the generator. RI is output, so it might wind up in your protocol where everybody can see it. So I'm monitoring your TLS protocol on the Wi-Fi network, and I also know your king. Now I want to predict what your PMS is going to be. So I see your client random, and I want to be able to figure out what the next few bytes of generator output you're going to produce are, PMS. So I have one block of RI from your client random, and you guys just told me I could go backward through this AES encryption. Yes?
So you want to find TI, right?
How do I find TI?
So after you decrypt RI, you can.
What if I told you
then
TI?
you have,
Yeah, no, you're good. What if I told you TI is the time in seconds? What's your strategy for finding TI?
You could calculate when you got RI and work backwards?
Yeah, there's not a lot of seconds, right? I mean, you just guess. Sometimes it's okay just to guess. So what we do is we guess. Like, let's say I saw on October 20th at 5:35 p.m. and 22 seconds, I saw you did this TLS connection. I just guess. Maybe your clock's off. Okay, that's a problem. Your clock might not be perfectly set. But big deal. If it's a time in seconds, I can go 60 seconds back or 60 seconds forward or 2 hours back and 2 hours forward. And I can guess TI. So you're absolutely right. We start at TI. We go through this AES encryption with our guess. We XOR it with this thing that we got by decrypting RI. And if we did that right, if we got TI right, wham, we get VI minus 1. We get the state that was used to generate that thing. And so now we have the internal state of the random number generator. And using the internal state of the random number generator and knowing TI, we can also go this way to get the next state of the random number generator. And if we can guess what the next TI is going to be, well, the next time this thing iterates, it's going to take this and put it over here and feed in a new TI. And we can actually just keep going. The only unknown here is the value, the timestamp that's being used at each iteration of the generator.
How do you know that you actually got the right VI minus 1 that you're looking for?
Good. Very good question. How do we know? It's a good question. So let's say I got 2 RIs, consecutive RIs, 2 outputs. Okay, the first one is the one I used to do this test. And I guessed TI, but I don't know if I guessed TI right. I might have gotten everything wrong and I've got the wrong thing. But I do have a second RI out value that I stole from this protocol. So I got 2 of them in a row. How do I do a test to see if I got TI right?
We can compute TI again.
Yeah. So once we've got our guess for what the first TI was, the first, let's call it T1, right? We just compute what the next let's call this, I guess, V2. I'm not sure what we're calling this. We compute the next internal state. We place this here. We make a guess for what the next timestamp is going to be. And we follow this all forward to get an output. If the output is the same as what we actually saw in the protocol, we guessed everything right. If the output is different, then one of our timestamps must be wrong. And so there's 2 timestamps we have to guess, because there's 1 timestamp is used for each output block. And so we have to guess the first one that was used to generate the first half of this. And we have to guess the second one that was used to guess the second half of this. But once I guess those 2 timestamps, assuming the guessing space is not very large, I can first take this first output, get the internal state, use the internal state to generate the second output, see if I get it right. And if these things are 16 bytes long each, that's 128 bits, the probability that I'm going to get a false positive here is very small. So if I guess the timestamps wrong because of the way AES works, the probability of getting a false positive is going to be like 1 over 2 to the 128. It's going to be very, very small. So either I get it right or it's completely wrong and I just have to go back and try. Okay, so if we're assuming times in seconds, it's even better because chances are that the timestamp hasn't even incremented between the first and the second output block, so they're probably going to be the same timestamp, so there's even less guess. In point of fact, a lot of devices that implement this protocol use get time of day. Anyone know in Unix type systems what the resolution of a get time of day counter is?
10 milliseconds?
Well, maybe, but what's the official return resolution? Well, it gives you back time in seconds and what? Seconds and microseconds. How many microseconds are there in a second?
1,000.
Times it with 6?
A million, yeah. So a million microseconds a second. And actually, this makes the guessing problem a lot harder. But when you think about a million, we're human beings. We're inclined to think of a million as being a large number. Well, when you write it as what it actually is, which is about 2 to the 20, computers can go through 2 to the 20 pretty quickly. So that's basically saying that each of these timestamps has about 2 to the 20 or 20 bits of entropy in it. If you have to guess 2 of them, it starts to add up. You're at 40 bits, but maybe it's not really going to be 40 bits. Why is that?
Because only a few bits will differ. I mean,
Yeah, because the first one may take you 2 to the 20 to guess. But if these things are generated inside a computer, probably the second block of output was generated like a millisecond or 2, or a microsecond or 2 afterwards. So this is going to be really simple. Okay, so now we have a strategy where if somebody is dumb enough to reuse the value k, you will be able to, from a 16-byte block of output, recover the internal state of their generator, and then predict all future outputs of that generator. Now, who would be stupid enough to leak the value k that they use for their internal random number generator? How would that happen? How would you ever get k? If somebody built a cryptographic device, how would it be possible to get k? Right, you guys know you have to pick your keys randomly, right? You could just pick this one on startup using a real random number generator. But what if you didn't? What if you were lazy? What if you didn't read the standard all the way through and you thought it was okay just to have this v value be random and you hard-coded k? And you left it inside your code. And then you had your code certified by a government standards agency, which required you to write a document that says, where did you pick all your keys? And you wrote, we hard-coded k. And then you submitted that to a public website where anyone could find it. And then it turns out that anybody who gets your code after reading that document can reverse engineer it and pull out the value k. Now we have a real kind of working attack. Let's go back to TLS and look at how this would impact you if you're doing this with TLS. I get 16 bytes of this client random, and I get another 16 bytes from the second half. This is R1 and R2. I don't know the timestamp, but it turns out that there's a really nice hack, which is actually a little bit uncomfortable, which is that the first 4 bytes of each client random are actually the time in seconds. So we are down to just guessing the milliseconds part. That means we actually lose a few bytes from here. We only get like 12 bytes of R2, but that doesn't really make too much of a difference, because then we're just using that to check and test. So we get that, and that means that the next thing we expect to see the client's random number generator spit out is 48 bytes of pre-master secret. So once we get the internal state and we check that it's right against R2, we just wind it forward 3 times, 16 times 3, and that gives us the pre-master secret. And now we can decrypt. It does the same thing if we're doing Diffie-Hellman. In Diffie-Hellman, the protocol looks almost exactly the same, except we now have client random and something like G to the A, G to the B. What is it that the attack would recover here? What are we trying to recover? If I get your client random, this is your client, your server. If I get the internal v value and the k value that were used to generate all your random numbers, what could I recover here that would make this totally insecure?
B.
Okay, yep, that's exactly right. So if I see you generating client random, then probably the next thing you're going to generate is b. And what happens to Diffie-Hellman when I can recover your b? Exactly. If I saw G to the A go over the wire because I was eavesdropping, I compute G to the AB, and it turns out that this secret is, everything else is just based on that, and other stuff you can see plain text. Okay, so it turns out that one of the vendors that did this is a company called Fortinet. I'll show you, let's see if I have a chart here. So a lot of people got this wrong, but here's a list of companies that basically got this wrong. Most of them don't really matter. Fortinet actually does matter because they're one of the larger VPN devices in the country. And let's see if I can show you the overall summary chart. I wish we had cooler things. But if you scan the internet and look for devices that say that they're Fortinet devices, these are just devices that answer. You scan on port 443, you can see that there are about 29 million devices that will respond to a scan. Only about 114,000 of them identify as Fortinet devices. If you go ahead and you try to run this attack, so you actually make a TLS connection to those devices and try to attack your own TLS connection using this technique we just described, using the known key that you pull out of the firmware, it turns out that 23,554, you can actually recover the key and completely decrypt that connection, which means any connection, any VPN connection these devices make is totally insecure against somebody who knows that this attack exists. So this is one of the pitfalls of random number generation is if you use a vulnerable random number generator, and it's very easy to do that, some really, really bad stuff can happen, and all of these devices, which are used by like banks. We had one incident where we were scanning and we actually hit an oil pipeline controller and knocked it offline, but it was also vulnerable. So a lot of these devices are completely vulnerable and the crypto is broken, not because the actual crypto protocol is broken, but because they're relying on random numbers from this not very securely implemented construction. Okay, so this is what I wanted to talk about. It took a little longer than I thought. But good, it let me talk a lot about TLS, which is what I want. Okay. So what I intended to talk about today was the TLS protocol. And I'm very happy that I've gotten to do most of that. But let me actually pull up what I was really going to talk about. Oops, that. Hang on a second. Okay. Good. So what we're going to start talking about today, or we already have been talking about today, is the TLS protocol. I want to see this multi-ported out. Okay, good. So TLS protocol, we've gotten a weird little introduction to it. TLS is mostly used to encrypt TCP connections. Why? Why is TCP mostly used to secure reliable protocols like, why is TLS used to secure reliable protocols like TCP? If you were designing an encryption protocol, what would be the difference between a reliable protocol like TCP and an unreliable one like UDP? People who took networks last year, I hope that one thing you came away with is the difference between TCP and UDP, because come on, you had to. Yes?
It's just that, like, with a reliable one, you know if the data was transferred.
Good. So if I have a reliable protocols model, a stream of data, you may lose, the connection may drop, but you're not going to lose bytes, at least generally speaking, you're not going to lose bytes. With an unreliable protocol, what is the basic unit of data? It's not a stream anymore. What is it? Datagram. Yeah, datagram. It could be a frame at a lower level, but like usually when we talk about IP, we talk about packets. And so what is the guarantee? What are the guarantees we don't get? We don't get guarantee that we're getting data in order. We don't get a guarantee that we're getting the data at all. And so when you're building a crypto protocol, that makes a big difference in a lot of different ways. If you're not getting the data, then you're going to have a really hard time reconstructing and doing useful things with it. Okay, so SSL TLS, the standard version of TLS, is designed to work with a reliable stream-oriented protocol. It's almost always used over TCP, though you could use other protocols. It's also a public key protocol, which we've already discussed. It doesn't require pre-shared keys, although there are modes of TLS that do. The most famous place that it's used is, of course, HTTPS, secure HTTP, which, what is HTTP at a low level? What does it look like? What is it, basically? It's a very simple protocol that uses pure binary representation over a UDP channel. Somebody just correct me. What does HTTP look like? Come on, you guys have looked at an HTTP protocol response, right?
I mean,
it's just text,
yeah.
Right? It's just a bunch of plain text. You could tell that to an HTTP server. It's a bunch of plain ASCII text sent over, not always ASCII text, you can use different encodings, sent over a TCP channel. So it's very easy. If you have something that can be layered on top of TCP and secure it, you basically have a secure TCP channel using TLS, and that gives you a very simple way to put protocols of HTTPS over it. Where else do you encounter TLS? What other protocols are secured using TLS? Anyone have any examples of protocols that might also use TLS? TCP-based protocols we use a lot. How about that? Good, SSH. SSH, so Telnet, which is the insecure version of SSH, was turned into SSH, but that happened kind of independently of TLS. So you could use TLS over a Telnet connection, but we developed a whole separate protocol, SSH, to do that. What other protocols? FTPS, good. What else? There's a big one I hope you guys are thinking about. Right, so when you get, I'm trying not to say the word. Email. Where is emails? Where are the security issues in email? Where do they occur? SMTP, very good. Now SMTP is used for two purposes typically. Anyone know what those two different applications of SMTP are? It's used between two different kinds of node.
It's the sender to the first email server and the first email server to any subsequent email server.
Good. So if you're using a mail client like Apple Mail or whatever, and you send an email, you're going to send it to Gmail, for example. That'll be one hop. And then once it gets to Gmail or to any other mail provider, it again uses SMTP to send it to the next mail server, the one that it's actually delivering to. These can both be secured with TLS. Not necessarily, though. They're not always secured with TLS. It turns out that the ones in between mail servers do not always get encrypted, which means they're much more vulnerable. Email is fundamentally kind of a vulnerable protocol. Usually the ones between clients and other servers are. I don't know if it says 2008. Okay, so we have our threat models in TLS. We care about the passive adversary because the passive adversary matters, but we also care about the active adversary because when you're trying to secure something going over a Wi-Fi network, which we now know not to be very secure, we are concerned that people could not only intercept our connections, but also modify them, change data at will. So we really care about these very powerful adversaries. Okay, let's talk a little bit about the history of TLS. Okay, going back, it's an old protocol. It was originally known as Secure Sockets Layer. Back in 1995, Netscape invented this. I don't know if anyone remembers Netscape. Okay, yes. Yeah. Oh, you're just raising your hand. Yes, good. I'm glad somebody remembers Netscape so well that they actually raised their hand to say that. Version 1.0 was never released. It was non-public. Version 2.0 was the first public version. It was released in 1995. It had a lot of problems that people pointed out. One of them was this funny idea that there were going to be export weakened keys included in the protocol. What this meant was that if you were going to export software overseas, it had to be limited to a 40-bit key maximum. And so that meant they actually had to build all these features in the protocol so that like American US servers could talk to non-US clients and still work securely. They would actually negotiate whether they were going to use strong crypto or weirdly weakened export crypto. We'll talk about that in a minute. Finally, in version 3 came out in 96, and some people found some smaller flaws. And TLS version 1 came out in 99. They changed the name because Microsoft refused to participate if they did not change the name to Transport Layer Security. But otherwise, it's just the next version. So we get confused. People say SSL and TLS. I don't know, these slides are a little old. So TLS 1.2 is the current version. Okay, it's a very flexible protocol. This is good and bad. It means that all kinds of different implementations can talk to each other with different options. But there are too many options. This is a big problem. One of the biggest features that this protocol has is the notion of backwards compatibility. What this means is if I'm running a TLS1 client, and you're running a server that supports, say, SSL3, or maybe it's TLS 1.2 and TLS 1.0, we should have the ability to still talk to each other. That seems really useful. What's the pitfall of having this kind of backwards compatibility where different versions can talk to each other?
If you can interfere with negotiation, you can negotiate down to a weaker form of crypto and then attack that.
Good. So what this means is that the security you get from this is basically the lowest common denominator. And if there's an attacker in the middle, they can sometimes manipulate this to cause both parties to unwittingly downgrade even to the weakest protocol that they both support, like SSL2, and all of those older attacks that we thought we'd fixed now become live again, and we can actually use them. This will come up a little later. Okay, so we go through about 5 different steps when we make a TLS connection, which we do every time we go to a secure website. Okay, so the first step is called negotiating peer capabilities. Okay, peer capabilities refers to a couple of different things. First of all, we say something like, I speak this version of the protocol. We list these things called cipher suites. What's a cipher suite?
It's like the encryption mechanism that the client supports in That's the case.
Good. Why do we have different encryption mechanisms? Why don't we all just use AES and whatever?
Because the server has to have the same thing in order for them to communicate under the same cipher.
Good. So one of the early options for this, one of the early design requirements of SSL and TLS was the expectation that different versions, different implementations would speak different crypto. That people in Japan would want to use the Camellia cipher for some reason. People in the US would want to use AES. People all over the world would want to use different algorithms, and some servers would only support maybe weak crypto because they were like embedded devices and so on. So what they came up with in this early design phase was this notion of a cipher suite. And the cipher suite actually refers to 3 different pieces of information. Okay, typically, the first part of a cipher suite is the key agreement protocol. This includes something like Diffie-Hellman, RSA, or elliptic curve Diffie-Hellman. We haven't talked about elliptic curves yet. So we have the key agreement protocol, then usually an underscore. Then we have the symmetric encryption protocol. So maybe I should spell these out. Key agreement, symmetric encryption. That could be something like AES CBC, which you guys are familiar with, followed by a hash function, which is going to be used. I don't know why I'm writing this. That is also a hash. Okay, fantastic. So these 3 things get grouped together into a package. You don't get to individually pick all of these. You have to pick a key agreement protocol, a symmetric encryption protocol, and a hash as kind of one package. Okay, so what happens is that the client, when it makes a connection, lists all of the cipher suites it supports, and now the server gets to pick one of those. If the server doesn't have a match, then it could just fail, but it picks the one that it thinks is the best. Okay, so it says, I speak this current, SSL 3.0, I support cipher suite X, and they both can have client certificates. I don't know why the server would say it doesn't have a client cert, but they can basically say what kind of cert they have. Okay, so they can negotiate what they're going to do next. Okay, the next phase is that these guys, we're going to talk about the RSA protocol here because this is the simplest one. They're going to exchange a handful of messages. So I mentioned this client and server random. I'm going to call them seed 1 and seed 2 here. Okay, so the server is going to say, here's my random. And the client, I'm sorry, I've got this all backwards. The client is going to say, here's my random. And the server is going to say, here is my certificate, which is a public key, as well as the name that everyone thinks I'm connecting to, as well as the date of expiration and so on, along with the server random, which I'm calling C2 down there. Finally, this client is going to do this thing we already have up here. It's going to generate the pre-master secret, which I'm calling C3 for some reason. It's going to encrypt it under the server's key and send it over the wire. The server is now going to hash together these 3 seeds, the client random, the server random, and the pre-master secret, to get a session key or get a master secret, which we'll actually use in communication. And then finally, we use that to actually communicate. Typically, we derive some other keys, but this is simplified. Okay, so this is the entire protocol. Okay, eventually, we may reach a point where we've used this key we agreed on for a long time. And so at the end of that time, we have a protocol where we can basically say, this key's expired, let's run the handshake again to get a new one. But generally speaking, that's a very long, long time. Okay, there's this other mode that we can also do, which is called resumption, where if we stop the connection, we can both cache our session key so we don't have to do a little handshake to start up again. This is called session resumption. So we can do this basically to save public key operations. And many systems do that. So these are the basic steps of SSL and TLS. So let's go back in time and in the last few minutes look at some of the old attacks on SSL v2. Okay, so there were a bunch of really, really terrible problems in SSL v2, but the biggest one was the following. The cipher suite list, and if you remember, the cipher suite list is sent from the client to the server, was not authenticated. So, what does that mean an attacker can do? An attacker can modify any of those messages going back and forth between the client and the server to change them. So what does that mean? Well, I could basically say to a server, hey, I only support this very strong AES-based cipher suite. And an attacker could then turn that into, actually, you support the cipher suite, which is called RSA null with null, which is no encryption, and no hashing. There's actually a valid cipher suite in some systems. Or more commonly, it could actually switch me from real encryption down to this export weakened encryption. To the server, it would appear that I was asking for export weakened encryption. I hadn't asked for it, but that message wasn't authenticated, so the server had no way of knowing what to do about it. It would just think it was legit. And the problem is this all happens early on in the protocol. Right? So it actually happens even before we've kind of exchanged keys to authenticate anything with. How do you authenticate this cipher suite list when the server and I don't share keys? Right? So the natural answer would be the client should MAC its cipher suite list, the one it's going to request. But I don't share a key with Amazon. How am I going to do a MAC? What am I going to do to prove to the server this is legitimately me, not an attacker changing my cipher suite list? What could happen? What could I do? It's kind of a thorny problem, yeah.
Use digital signature.
Okay, if I have a signature, I'm a client. If I have a signing key and a public key, and the server knows my public key, then I could sign that message. That would be good. But does Amazon know your public key when you connect to it? Generally speaking, unless you have a pre-existing relationship with Amazon where you've like given them your public key, you don't have a public key established. Now you could, in the first message, you could give them your public key, but then like, right, how do they know it's really your public key? Well, you could get a certificate authority to sign it, but you're right, if I have a signing key, that might work. But what if I don't? What if I'm not authenticating to Amazon? What could I do? Looking at this protocol, so we have this protocol where it's client random, server random, this encryption, ultimately we do some encryption. And what's happening up here is we're adding to it, the client has a cipher suite list, which is just going right here in plain text, not authenticated. How would you guys check that that cipher suite list isn't being tampered with, assuming the client doesn't have signatures, doesn't have a signing key? What could you do? I mean, the attacker could just change it. It seems really bad. But there is a way to fix it, and it was fixed in SSL version 3. Any ideas? Okay, yes?
Like, have the server send it back to confirm that that's what they...
Okay, but what if the attacker changes the one that comes back? Seems really thorny. Okay, we do not have a key, we do not have a MAC key here. But what about down here? We do get a MAC key eventually, right? Because eventually, if we complete this protocol, and we get all the way down to the bottom, we're going to have arrived the shared master secret from which we can derive a MAC key.
Could we specify a minimum standard? In other words, I'm willing to use this strong one, this almost strong one, but I'm not willing to dip below this level?
Good, okay.
So if something comes back, you just reject it?
Good, so if we can specify, if we can assume that the server is not going to take like a really bad choice, right? There's going to at least, whatever it picks, the attacker might be able to downgrade it, but whatever it picks is going to be at least a little bit okay. Then we can say, okay, well, let's just assume that whatever the attacker does to change our cipher suite list, at least the key we arrive at here is going to be secure. It's going to be only me and the server have it. Now what could we do? Retroactively, what could we do? Right, we want to make sure the cipher suite, we want to make sure there was no tampering. Like you just said, it's a minimum standard. It might be good enough to get down here and do one MAC, but that's all I can really trust. I'm not going to go ahead and encrypt anything with it because it might be really broken for encryption. But let's say I trust it just to get down here and check a MAC. Now I share a key. Yes?
You could ask again, hey, what's the list we could check to see what they agreed on. We told them we agreed on what we actually want to agree on and agree.
Good. So if we trust the key agreement protocol enough that we think it's, even if they change the cipher suite list, no matter what they pick, it's still going to be somewhat okay. We can go ahead and run whatever gets picked down to here. Once we have a shared key, then we can use a MAC to securely and authentically talk to the server and say, by the way, here is what I saw, and here is what you saw. Let's compare notes. And in fact, that's one of the last things that happens in the real SSL protocol is that the two parties actually exchange MAC'd messages. Let me erase and actually rewrite because it's not there. Is this guy basically says, here is a MAC computed on a hash of all this stuff.
All this stuff being the the cipher suite?
All previous messages from both sides.
Okay.
And so the two sides, and then the same message goes back across. This is called the finished message, where both sides, having agreed on MAC keys, now exchange their view of what they saw in the protocol. And the idea here is if somebody tries to tamper with any of these messages, the two sides will not agree. The hashes will not be equal of what they believe the messages received were. And if they get a secure MAC key, they can now compare notes with this authenticated, these messages down here, and they can verify that there was or was not tampering in there. Yes?
Is this implementation okay where we mandate the chain circumspect message after all this is done, and we just say that now let's use this circumspect, and this is, and because the chain circumspect message comes later on, it will be authenticated or.
Yes, it should be authenticated. However, even that can be tampered with sometimes. What she's saying is that there is another message in here that actually turns on encryption, and there are attacks on that that can actually disable that message if that's not authenticated. And that was the next thing I was going to talk about. But since we're at the end of class, I'm going to save that for next time, and we'll start off with the kind of attacks on different versions of TLS, and we'll continue with that.